After understanding the second order differential equations for its particular integral and for its complementary function, now we can extend our analysis to the next level, and that is to extend it to the higher order differential equations. Primarily we should solve it for the particular integral, and before that we should get clear about its standard form, and we know that it's going to be an nth order differential equation, and n should be greater than 2 because now we are talking about third order, fourth order, and so on. So the standard form is as it is in the case of second order differential equation, where we introduced the concept of higher order differential equations but limited our analysis to n is equal to 2. But now we are keeping it n greater than 2. So now n can be greater than 2 and can reach any positive number. The observation is that the order of the derivative increases when we go from right to left. As you can see, this is the original function, this is the first derivative, second last derivative, and the last derivative, or the highest derivative. Whereas if we look at the subscript of the coefficients, they are increasing from left to right, as we started with a naught and we are ending at an. The highest order subscript is appearing on the right hand side, and the b is the constant term on the right hand side, as we have been observing before. So let's come to the solution of it. The first part would be the particular integral, and definitely the second part would be the complementary function. However, this video is devoted to the particular integral only, and in the next video we will see that how we can calculate the complementary function. So let's get to the main objective of this video. This is the particular integral, and it can be well understood if we build it on the second order differential equation. This is where n was equal to 2, and now what we have is an order greater than 2, so it's nth order where n is greater than 2. What we have done here is that we have built those three cases or subcases on the basis of the second order differential equation subcases. We remember that in that first subcase, a2 was not equal to 0, was non-zero, in other words, where a2 can be considered as the highest order subscript constant. So in the same way, the highest order subscript coefficient would be non-zero in the nth order or higher order differential equation, and there is no restriction on the second highest order subscript coefficient. Here the same thing is visible, no restriction on the second order highest highest subscript coefficient. So the formula was the constant on the right hand side over the highest order subscript coefficient, and here the same holds. The highest order subscript is appearing in the constant in the denominator, so they are linked with each other. In the same way, here the highest order, let me make it simple here, I can call it highest order coefficient. Now highest order coefficient is 0, and here again highest order coefficient is 0, so it is the second subcase which is interconnected, and the second highest order coefficient, which is constant in nature, is non-zero here, so it is also non-zero here, the second highest order coefficient. And the formula was that second highest order coefficient was appearing in the denominator, and here again it is appearing the second highest subscript coefficient is there. But when it comes to this third subcase, both of the highest order and the second highest order coefficients are 0. Here the same situation will happen, that is the highest order coefficient and the second highest order coefficient. Here we divided it by 2, but here this is not as simple or as straightforward as the first two subcases were. We remember that in the background of this we developed the formula by using the assumption that y is equal to k, a constant. And in the second subcase we developed the formula on the basis of this assumption that the value of y, that is its solution, is some sort of variable, that is k into t. And in the third case we assumed that y is equal to kt square. So it's also a variable but with a degree 2. Here we are going to use the same thing, that is the assumption behind the third subcase. For reminding yourself about these three assumptions regarding the particular integral formula derivation, you can refer back to the particular integral development of the second order differential equation. It is present in that video. So we are going to use this because right now we don't know about the order. It can be 3, it can be 4, it can be 5 or any other value. So we are going to use this y is equal to kt square as the trial solution that we have already used in the second order differential equation. So in this way we can come up with the second order differential, the third subcase of the higher order differential equation. It can be well understood with the help of some examples. Here we are going to do this. The particular solution is to be found of this certain example in which b is 24, a4 is 8, a3 is 16 and a2 is 14 and a1 is 6. So we have extracted all these values here, and an is equal to a4 which is equal to 8 and it's not equal to 0. So yp is equal to b over an. We are using this formula because the highest order coefficient is not equal to 0, and we remember from the first case that when this happens we apply this formula. So we are going to apply this formula. It is also non-homogeneous case because b is not equal to 0. So we will see the substitution, which is very much easy. A4 and b, both of them are substituted and we finally get the particular integral of the given differential equation, which was this one. It is a static equilibrium because yp has a constant value. We can't see any t or any other variable in it. Now let's come to another example from the book of Alpha C. Chiang, and in this example you can see that we don't have yt term in it. It means that the highest order coefficient is equal to 0. So it is equal to 0. Here you can see it's absent, so definitely its coefficient should be equal to 0. Here we have generated this thing just to be more clear about it, whereas other values like a1, a2 and b, they are also highlighted. So when we see that the highest order coefficient is equal to 0, it means that the second subcase would be applicable, where the second highest order coefficient comes in the denominator. So in this non-homogeneous case we are going to use this formula, which is adjacent to the second order differential equation, second subcase, and definitely by putting these values of b and a2 we get the final answer, which is the particular integral of this differential equation which was given. Final example is the third one, which is again borrowed from the book of Alpha C. Chiang, and in this case you can clearly see that the first order derivative as well as the original function, both of them are missing. Therefore we have to put some 0 value instead in their coefficients so that they actually become 0 in the given situation, whereas a1 and b, they are already extracted. So we extracted all of these values here, and this is non-homogeneous case. This is b is equal to this is yp, which is equal to b over this has to be not applicable because we don't have the same situation. Both of them, that is the second highest coefficient and the highest order coefficient, both of them are 0. So neither this nor that will be acceptable. So this correction has to be made here. After making this correction, let us see that how we can do this. As you remember that in the subcase 3 we used the trial solution. This is the trial solution, y is equal to kt square, which means that its first derivative will be equal to this, and the second order derivative will be equal to this, and the third order derivative will be equal to 0. Now if we have all these values, I can put all these values in the given differential equation. This is the given differential equation, which after substitution it will appear like this: the highest order derivative, the second order derivative, the first order derivative, and the original function. Now we can extract the value of k from it because it is easily getting extracted. It is equal to 1 over 18. You can pause the video and solve this. Now we have the value of k, so we can plug it back into the trial solution to get the final answer of the particular solution. So instead of k, I'm going to put its value, which is found to be 1 over 18. So this trial solution now has become the particular solution because there is nothing unknown in it, and it has satisfied the equation. As you can see, this equation is satisfied. So the solution actually satisfies the equation, and it has happened. So we can consider this as the particular solution of the given differential equation, which is this, and it is a moving equilibrium because it contains a variable, so we can call it a moving equilibrium. So this is how we can solve the three subcases of the higher order differential equation, in which we have found that the order can be greater than 2, and we can solve it by using this set of formula, and this can allow us to deal with situations where we have higher order differential equations. And in the next video we will learn that how we can calculate the complementary function of the higher order differential equations. Thank you.